Hello and welcome to another episode of Matt Pokes and Prods at Things. We're back at the electronics desk where we should be, and also back is this NES that I repaired a few episodes ago. You can see what remains of that right here. That video was actually the last time that this board worked, and I've not been able to get it to boot anything since. So there's still something else going on. And I've spent a few hours with this thing. At one point I thought the CPU was dead, so I clipped it out, desoldered the pins, threw in this socket so I could just drop in a replacement whenever I want. I fiddled with the lockout chip for a while. This should be soldered to ground, but that's come apart. I replaced these two caps. That didn't do anything. I cleaned up the board with a bunch of simple green and a toothbrush yesterday, which was good in its own right because this is the backside of this board was just fucking gross.
Previously on Matt Pokes and Prods.
This shit is gross. It is gross as sin.
And now, the conclusion.
So you can, I doubt you can see it in the video, but you get a better idea of where these traces have gone a little bad. It's also allowed me to figure out my way around things a little better. But what I've observed on the scope and is my theory. I've watched the address lines and I've watched the data lines. And, they flicker for a bit and then they just go dead. Like, the entire CPU stops. And the only thing in the 6502's opcode arsenal, and technically I do not believe it is documented, are a few opcodes that are a halt command. They bring everything to a dead stop. CPU stops reading instructions, stops executing instructions. It just doesn't do anything at all. My theory is it's not getting the data off of here right. There's either a mechanism on the NES that's like, shit, nothing more we can do. Can't get anything going, so just crash before you break or hurt yourself. Or by some random, like 1 in 256 chance, technically less, because there's like half a dozen or more opcodes that are effectively a halt. That in a 256 chance, that is getting one of those halt opcodes by reading everything wrong. Yeah, and I'm at my wit's end. So last night I had an idea. What if I just hooked up a microcontroller to the address and the data lines and went through it one address at a time, reading, writing, and verifying that everything is as expected. And before I get into the microcontroller side, I want to actually prove that works at all. So what I'm going to do is I'm going to take melty breadboard and I'm going to hand wire up a few addresses and have some LEDs to show the data coming out, just to make sure that this idea works. And we're going to go into time lapse on that now. Alright, we are back. Everything is hooked up. Yeah, so what I've done here is the red and blues, these are address lines 0 to 15. Basically I hooked them to either 5 volts or ground. That's 1 or 0. Respectively, the address I have plugged in right now is FFFE, which is the interrupt vector. When you turn on the system, it looks at FFFE and FFFF to figure out where in the program code it should start executing. So yeah, I've got might actually have that wrong depending on if it's MSB most significant byte or least significant byte on the address lines. I'm imagining it should just be like this is bit 0, this is bit 15. That's whatever. The data bus, I have the gray and white ones here coming out. Those are this is D7 and I think this is D0. So hopefully that'll give us a representation of the address that we're currently reading on the bus. Rewrite I've pulled low. I don't have the docks for that in front of me. I'm pretty sure low means that we're reading. And then we got 5 volts and we got ground over here. So without further ado, I'm going to turn this thing on and just watch it explode in my face. Or, you know, nothing is a pretty good option, too. Please stand by. Alright, we're back. It's been a little bit. I'm sure the lighting has changed because the sun's gone up more. Did a few things. The first thing I did was hook up my logic probe and check to see if I was getting anything off the pins coming out of the data lines, and the answer was yes and no. I had a bunch of floaters. Couldn't figure out why. I was like, oh god, everything's awful. I swapped out these resistors from 330 ohm to 100 ohm because I decided, yeah, maybe I should do the math and make sure that's correct. The reason I did that is because when I was measuring using the multimeter to measure the voltage coming off the data lines, sometimes I would get 4 and then I would test it on one of these leads and it would drop to 1.5. So I decided, okay, maybe I should actually go and look at all of how the pins on the NES CPU work. And contrary to what I had assumed, the read-write pin is in read mode when that's high. Or rather, the bus is in read mode when read-write is high. And I had it pulled low because I figured, oh, write means is high. I don't know. Changed that. I also noticed that M2, this guy right here, that is the clock divided signal. So the clock goes in, internally it divides it by 12, and then what the CPU is actually clocking itself on comes out on this pin. And I guess all RAM reads happen, get back to that in a minute. All RAM reads happen when M2 is high, and it's entirely possible that that could be driving some chip enables elsewhere on the board. So yeah, I did all that, and I changed this around to not read from the cart. Currently it's reading from address 1, which is in SRAM here. And we get some stuff. It's a little flickery, that's fine. If I move this, I get a different value. I can, let's go to address 4. I find it hard to believe that on boot up, all of SRAM is, full of ones, or largely full of ones. It should just be random noise. But that seems to work okay. When I switch it over to read from the cartridge, I get some funky stuff. And we'll cut for that because it's going to take a minute to switch that over. Alright, we're back to reading address FFFE, which is the least significant byte of the reset vector. Yeah, we got all those out of whack. Power back on. And it just fades out. It does it consistently too. If I power it off, power it back on, I get some random stuff, but eventually it settles into, the exact same pattern all the time. Now, I also swapped out the cartridge. I put in my Super Mario Brothers Duck Hunt cartridge because it's a less complex system inside. I downloaded the ROM and I looked at the data, and this should be, this was supposed to be C? No, this should be 0. This should be reading 0. Now earlier I went, ooh, that's a thing I should check. When M2 is high is when RAM, I should go back and read the documentation, but when M2 is high is when RAM reads are done. So I'm wondering if I pull that low, if that will make the cartridge stuff work more better. I just need to figure out, this one is read write. This one's M2, let's pull it low. I can't imagine it's reading anything on a low, but all right. I'll bet you anything the actual verbiage was bus reads are done when M2 is high, because that's the only time that the CPU is doing anything. All right. So that leaves me in a little bit of a quandary. Let me read F. Ooh. So that is in theory the last byte of the second program ROM bank, and that should be 1 with 6 zeros after it. Clearly it's not. Something else is going on. Maybe this is the problem. I don't know. I don't believe I'm going to be getting to building my RAM reader in this episode. I guess I'm not, like, this is the thing now. I want to make these videos, so I apologize. Yeah, I need to figure out what's going on. It was just a little thing. Talking directly to everything on here. It's kind of fun. I think it's technically working. And hopefully it'll get me to figure out what the fuck is wrong with this board. Tune in next time when I do the thing that I actually was going to do and then didn't, because none of these are scripted and barely planned. Goodbye.
And now, the moment you've all been waiting for.
Well, god damn it, I lied. Shut off the camera and I started probing around on the RAM chips to I was making sure that everything that needed to be enabled for various addresses was actually enabled. That went down a rabbit hole of figuring out how the address decoder works, and that was too fascinating not to talk about. So before I sign off, I'm actually going to explain how that works. We're going to draw a chip here, a very large chip. This is a 74 LS139, was it? Yes, 139. 16 pin chip. 2, 4, 5, 6, 7, 8. Whoops. 2, 3, 4, 5, 6, 7, 8. We'll go ahead and number these. 3, 4, 6, 7, 8, 9, 10, 11, 12, 14, 15, and 16. Okay, so right off the bat, we take care of these. This is plus 5 volts. That is ground. And really quickly discussing with this, so this is a 2 to 4 line decoder. Basically, it takes a binary number in, and then it spits out that number on these lines. So a quick truth table would be pin 1, pin 2. Oh crap, I'm not going to have enough room for that. Shit. Please hold. Okay, welcome back. I've drawn this at a slightly more reasonable size, which is good because I'm going to be writing more stuff out here later. Back to our truth table. So we have, well, technically we have 3 things to keep track of. I'll talk about that guy in a minute. So yeah, it's a 2 to 4 line decoder. We have a binary number coming in. So let's say we have 0, 0, and 0, 0. I will clarify a thing in just a minute. This isn't going to be 100% factually true. So if we have binary 0 coming in, then it's like, oh hey, that's binary 0. And it turns that pin on. And we got like, oh, but I have binary 1 coming in. Alright, dude, let's turn that pin on. And so on down the binary, whoops. That chip is broken if it's doing that. So yeah, pretty great. Get a number coming in, and then you just turn one pin on for that binary number. Now, what actually happens here is these are active low. So if you have 0, 0 coming in, this is actually going to be 0, 1, 1, 1, 1, 0, 1, 1. It's just, this part is flipped of what I have written down, which is actually important, but not right now. And crap, I've muddled things up here. Anywho, so we have actually, there's two of these. This side has a decoder and this side has a decoder. And there's, each side also has an enable, which is what G is. So basically, if the this is also active low, so if it's a 0, it's turned on. If it's a 1, it's turned off. So in that case, if the chip is not enabled, it just spits back all 1s all the time. So on this side, this is the enable pin, and that is tied to ground. This side is always turned on. Then we have, this is technically the second side, so we have bit A and bit B. And according to my schematic, snap. This one is coming from that weird clock divided signal. So effectively, we'll get to that in a minute. And then 13 is coming from address line 15 straight off the CPU. And then 12 is unused. 11, this actually goes out to pin 1 of this chip. That's coming from pin 11, and this is the enable pin for that side. And we'll write down the truth table in just a minute. 9 and 10 are unused. That's not right. No. 10 is unused. 9 goes out the cartridge slot, and that is the ROM chip select. So really, we'll write out a quick truth table for this. We have A and B. And we only have, the only things we have hooked up are going to pin 1 and ROM. So if A and B are both 0, that's pin 12, doesn't do a goddamn thing. If A is 1 and B is 0, then we say, oh, those are high. Remember, active low here. So that becomes low, that stays high, and that turns this on, and we will get to that in just a minute. Oh yeah, recall that this is weird clock signal from the CPU. That's the clock divided by 12, and this was address 15. So if that's down, nothing actually happens because pin 10 is lit up in this case. So those are both high. And recall when I said that all reads happen when the modified clock is high? This is basically enforcing that. Because when we come down here, and both A15 and the clock are high, then we are talking to ROM. That pin goes high. So effectively, anytime A15 is set, and A15 would be, and you can think of it as A1 with 15 zeros after it, or address 8000. Anything 8000 or above is all talking to ROM, and this side of the chip is what makes that happen. All right, let's do the other side here. I realize I flipped my symbols. So this is 1A, this is 1B. Pin 4, this goes out to... These are all the outputs. So that goes to work RAM, chip select. Pin 5 goes to... pin 5 goes to PPU, chip select, and these two are unused. And these coming in here is give me just a moment. I'll make sure I get these in the right order. 3. So this is coming in from A14 on the CPU, and this is A13. All right, truth table time. We've got... So the first thing to note is this side will never ever be turned on unless this is high, or the clock signal's high, and we are not talking to the PPU address, or the, I'm sorry, ROM. Address 15 is low. So basically that's the first 16 kilobytes of addressable space. So that's important to note. And then we have a 13 and a 14 are our inputs. Oh Lord. And then our outputs are RAM and PPU. So right off the bat, if those are both 0, we are talking to RAM. If that's 1 and that's 0, we are talking to the PPU, and anything after that, camera took the moment I was stopping to think to shut itself off. You didn't miss anything, trust me. I'm just getting very confused because it looks like this is unneeded. See, we have, this is A1. If A13 is 1, that is talking to PPU, and I think a binary 1 with 13 zeros after it is 2000, and I remember from writing that emulator that all addressing to the PPU went over 2000. But the thing that's confusing me here is if we have 01 or 11, nothing's done. And there's nothing hooked up to either of these pins, so having address line 14 hooked into this decoder chip is entirely useless. Like, there's literally no point. Yeah, no, that's buggered up. I didn't even notice that when I was figuring that out earlier. But yeah, so I thought that was kind of fun to see how this was all put together. You know, the clock, or having the clock force everything, or forcing actual enables on the clock. That's what I want to say. And then if A15, if we're not talking to ROM, then this is actually, this side of the chip is used to turn this side of the chip on, and then we can address low RAM and PPU. And we can actually infer some things about the memory map that way, based entirely off of this and not what everything else is actually hooked up to. This is 0000, and this is FFFF. We know that 8,000 and up is all ROM space. We have this chunk of unused space from, I guess, about 4,000. So that's going to be 2,000, and this is going to be 4,000. This is RAM. This is PPU. Technically not, and this is just no man's land. PPU actually only has 3 other address lines going to it from the CPU, so it's got, what, 8 addresses, 2000 to 2008. But yeah, this chip makes all that happen. And I thought it was fascinating to see it all put together. Hopefully you haven't been bored to tears. Hopefully this is actually legible. Yep. So yeah, this is the actual end of the video. The addressing largely seems to be working out in the lower half of space. The ROM space is kind of funky, and would actually knock the pins around a few times and I'd just lose all addressing. So yeah, that spring-loaded cartridge nonsense is just fucked up. I'm going to do some more poking around. We'll try to have a more coherent video next time. And at some point, I'm going to get around to making my address or my bus reader writer. Because I think it's still going to be handy in this case. But I actually have something useful to go off of now. Thank you for watching me ramble. And I guess I'll see you next time. Shit, God.